Hello, let me start this poster presentation with a bit of context. We have been sending satellites to space for decades. However, in recent years, the number of launches per year has grown exponentially. If this trend continues, collision risk may significantly constrain access to orbit. To address this, agencies and companies are preparing active debris removal and in-orbit servicing missions. For example, ClearSpace is planning a first European debris removal mission in the second half of 2026. These missions require autonomous docking with non-cooperative targets. For a spacecraft to approach and capture another object safely, it must estimate its full 6 degrees of freedom pose, which are both position and orientation, in real time. And this must run onboard unembedded hardware in the satellite. However, most state-of-the-art approaches rely on iterative PNP solvers, which are quite slow. According to prior work, they achieve around 7 frames per second, even on a desktop CPU with an RTX 2080 Ti. That is not sufficient for embedded autonomous control. So we asked, can we maintain similar accuracy while enabling real-time inference on edge hardware? We thus introduced FastPose-ViT, a 6 degrees of freedom pose estimation framework that avoids slow iterative PNP algorithms, introduces a representation we call apparent rotation, recovers the true pose analytically, and runs in real time on a Jetson or in Nano. Importantly, the Jetson or in Nano is already used in space-grade embedded systems. We achieve around 75 milliseconds end-to-end latency, or up to 33 FPS in an asynchronous parallel pipeline. We also achieve competitive accuracy on the SPID dataset, which is one of the standard benchmark in the spacecraft pose estimation community. Regarding the methodology, FastPose-ViT follows a 4-stage pipeline. The first step is detection and cropping. We detect the spacecraft using a lightweight detector and extract a cropped bounding box. The second step is post-prediction. The cropped image is fed into a ViT-B backbone, which predicts the translation and apparent rotation. We use a vision transformer because it captures global structure effectively and scales well with synthetic training data. The first step is geometric recovery. At this stage, the network predicts translation and apparent rotation in the cropped image frame. To obtain the final pose, we analytically map these predictions back to the full image coordinate system. We convert the cropped translation into the full image translation and the apparent rotation into the true global rotation. This is a closed-form non-iterative geometric transformation. And the fourth and final step is edge optimization. We quantize the model, optimize it with TensorRT, and deploy it on the Jetson or in Nano. The entire system is designed from the beginning for embedded deployment. Now let me explain the key idea. Apparent rotation. When an object is not centered in an image, perspective makes it appear slightly rotated. On a full image, a neural network can often learn this effect implicitly because it sees the object together with its full translation context. But once we crop the object, we remove most of that context. As a result, the rotation visible in the crop becomes strongly coupled to the object's position in the original image. We call the rotation that the network can reliably observe in the crop frame the apparent rotation. To formalize this, we derive a mathematical formulation that explicitly models this perspective effect caused by the cropping process. Instead of asking the network to predict the true global rotation directly, we ask it to predict this apparent rotation. Then, using our geometric formulation, we analytically recover the true global rotation. This simplifies learning and removes the need for iterative PNP refinement. Regarding results on the SPID dataset, we match PNP-based method in accuracy, and we outperform previous non-iterative approaches. But the key result is speed. On the Jetson or in Nano, we achieve around 75 millisecond end-to-end latency, or up to 33 frames per second in an asynchronous parallel pipeline. This is real-time inference on deployable embedded hardware. This makes FastPose-ViT suitable for autonomous rendezvous, servicing, and debris removal missions. To summarize, FastPose-ViT removes slow iterative PNP bottlenecks, introduces apparent rotation to simplify pose estimation, maintains competitive accuracy, and enables real-time embedded inference. It bridges the gap between academic pose estimation and deployable onboard autonomy. Thank you.